Okay, so today the topic is interesting. We're starting with artificial neural network. So far, we were working on the big field, which is called machine learning. Now, machine learning has many parts. Sub-part of machine learning is called artificial neural network. Okay, so artificial neural network is machine learning, but it's different in the sense that the way you construct or the algorithm, how they work is completely different than the other one earlier that we talked about, like decision tree, KNN, and so on and so forth. Let's skip this part. So artificial neural network depends on the idea of mimicking the brain structure. Like a human being, usually, I mean, if you check or if you look into innovation, actually it's not the innovation that human beings come with, they are not completely out of the blue, right? They try to mimic other, let's say, creature like the airplanes. We come mimicking the birds, right? So people or human being look forward to be able to fly like the birds. So when they come up with the airplane, they are mimicking how the birds look like, right? So the point is, we as a human being, we mimic many things in order to come up with solution for problems that exist in this world. Now, one of these things that we try to mimic here is trying to mimic the brain structure. So brain structure is a bunch of, not a bunch, is millions of neurons are connected to each other. Okay, so the idea came in last century. Again, ANN or artificial neural network is not something new. Okay, though it's become, I mean, famous just in the last decade or last 2 decades, but actually the idea was there quite long time ago. But because of shortage of power, we didn't have computing power much. And also, of course, for other obstacles, like how to train these neurons. So actually the idea went like in hibernation, like it has stopped for a while until the idea came back maybe after 1990s or 2000, where we had enough computing power and also the algorithms for training neurons have become more mature. I mean, the ideas came in later. Okay, so, okay, I don't want to proceed further first because we need to go to the activity. Then I can go further. So all of you ready? Okay, now since you are expert, right? Now this is week 10. Another 3 weeks probably we will conclude this course. So I need from you two things. The first thing, write an example, as now you should understand what is the difference between traditional programming and data mining. Write an example that demonstrates how machine learning or let's say data mining is different than traditional programming. Okay, and using, if you remember, we had 3 parts that compose any application or any solution. Do you remember? Data, rules, and answers. So keeping these 3 in mind, draw 2 figures. If you remember, also in week, the first introduction, we had it, but please don't look. Try, see what you can recall. Draw 2 figures. One figure is about resembling the traditional programming. The other one about data mining using the 3 parts I mentioned. Data, rules, you remember the circles? We drew data, rules, and answers. Plus, after you finish drawing, write an example to explain these two. Just like any example comes to your mind to exhibit the idea that for these drawings. Is it clear or you would like me to repeat? Repeat. Okay. So again, remember the circles we drew at first when we were explaining the difference between traditional programming and data mining? So I need from you to use these 3 parts, the circles, if you remember, data, rules, and answers. Use them to draw 2 figures, exhibit traditional programming and data mining, and then support your drawing with an example. Okay, you can go ahead. Don't look back. Try, up to you, but It's better if you don't look, but if you like to look, up to you. Up to you. And then support with an example. Now you should be expert, right? If anyone asks you, you should tell what is the difference between traditional programming and, or at least other system, normal system that we knew a long time ago, and between AI systems, artificial intelligence system. Okay, so go ahead. You have 5 minutes. Then your friend, I'll tell you how to swap the paper, should give you a mark for your answers. So you're going to be a student and examiner at the same time. Example, ready? Okay. Finish. Transparent, 100%. Oh, hi, you're here. Okay, welcome back. For those who are struggle, if you like to look back to the slides, can. You still need to write an example. You can look back, but prepare your answer sheet. Okay, another 2 minutes. Okay, done? Anyone needs 1 more minute? There's some people still writing. All right, this is fundamental question. ABC question. Because at least you should know for now what is the difference. Okay, hurry up, take piece of paper. Piece of paper. Don't have piece of paper. Or maybe you write on your iPad, but hurry up, you have 1 minute. All right, piece of paper, you have? Piece of paper and pen. Okay, then draw 2 figures showing the difference between data mining and traditional systems. Remember the 3 parts, data, rules, and answers. Draw 2 figures. Please, his friend, support him. 30 seconds left. And provide an example showing, explaining how these figures or these 3 components that explain the difference between traditional programming for traditional systems and AI systems. Now, hurry up, faster. No, don't look to the slide. It's not going to help because the question was orally given. Just draw two figures. If you remember week 1, we had talked about data, rules, answers. Just draw two figures showing the difference. Okay, 10 seconds. 9, 8, 7, 6, like we are launching rocket. 5, 4, 3, 2, 1, go. Okay, so you should remember this one. Now, don't mark yourself. Please swap the paper to your friend. Swap your paper to your friend and take your friend paper. Anyone choose fast, hurry up. Swap your paper to your friend. Please hurry up. Now, his friend or her friend, look to the figure here. Any mistake, deduct 1 mark. So the total mark should be 10. Any mistake, deduct 1 mark. Hurry up, you need to mark and give him and pass the paper back to your friend. So check here, this is on the left-hand side, showing you traditional programming or traditional system, and on the right-hand side, showing you the AI. Any mistake you find, deduct 1 mark. And check the example. Also, if the example given is wrong, also deduct another 1 mark. Sorry? It's up to you. You are now the judge. Decide. But please don't show mercy. Mistake. So your friend can learn. Okay? Anyone has got 10 out of 10? Raise up your hand. Anyone got 10 out of 10? Sorry, Clinton? Okay, great. Is it for you or your friend? You mean? Oh, your friend. Oh, okay, that's great. Stephen? I don't know who's referring to, just I said. Anyone got 10 out of 10? Who? Just raise up your hand. Yeah, raise up your hand. Why you're shy? And check the example, huh? Okay, give me the paper who got 10 out of 10, just I like to see whether your friend was so much merciful for you. Unless if you want to change your marks, where's the paper? Yeah, the rules need to be changed. This one. No, where's the paper? You mark, where's the paper you mark? This one? Where's the example? No example. No example. Then -2. Hello. -2. Hello. Oh, okay. Let me see. Okay, figure is correct. Study the problem and come out with a set of rules. But give an example. The example is not clear. Study the underlying pattern and data. Yes, I mean, this is general, but you need to make it simple. If a person, let's say your grandmother asks you, and then you tell her what you wrote here, I'm sure she wouldn't understand anything, right? If you tell her, studying the problem, come up with rules, study the underlying pattern, what pattern? Of data to produce rules. Yeah, so, okay, your friend was so much supportive, he gave you 100%. Great. What is ginger? Or general lang? I don't know what is it. Okay, So again, please, until now, if you're not sure, please pay attention. I mean, it's not logical. You come to this class, right? And after all simple question like this, you're not able to answer. So if you remember, this have shown the slide many times, right? I think this is the third time included. So in traditional programming, we have data, right? Like for example, let's think about an example. Like you need to calculate the tax, for example, right? Now the data is gonna be your income salary, right? Let's say the history for your income every month, right? And then the rules is well known, set by the government. You can look for the rules how to calculate the tax, right? If you are in a certain category, then the ratio for tax is going to be that amount. Then just you multiply with the income, you find the total tax number, right? Straightforward. So again, I repeat, you have the data, which is your income, salary, for example. You have the rules already been defined, right? You don't need to explore. You don't need to go and find out. It's well known. Just you go, maybe in USA, there's different ratio for calculation. For Malaysia, different ratio. But the rules is already there, set out by the government, right? You don't need to go and find it by doing data mining. So the rules are already there, and then you come up with the answer, right? Now, take another example for data mining. Let's say we are trying to calculate the car price, to find the car price. Now, data is there. Let's say the engine size, right? Let's say the manufacture date, and so on and so forth. We know the car. The car is in front of us. We know the color, the manufacturer, everything we know. This is the data. Now, how to calculate the price? Is there any rule or equation tells you how to calculate the price based on these features? Anyone can tell you? Nobody, right? I mean, go search on Google, look for the rule or calculation, or let's say the equation to calculate the car price. You won't find, because it has many variables included, and those even variables can change at any time. Like MCO, after MCO, before MCO, everyone knows cars price went up and down, etc. So the point is, there's no fixed rule to find out. Even from one country to another can change. Even in the same country, maybe 1 month now the price is like this. Another month something else may happen, right? Which may the car price goes up or down. So in this case, we have no rules, but we know the answer. The answer is the car price is well known. We can go to the car dealer and ask him about the price of the car. So we know the answer. We know the data, but the rule is not there, correct? There's no rule. If you go to the car dealer, tell him, please tell me why you are saying this is the car price is like this. He won't tell you. Maybe at least he will tell you this is the market price, right? But there's no rule there to tell you how to calculate. Here where data mining comes in to help you. Because once you find this rule, you become like the wizard, right? You can, without asking about the price for other cars, based on the features, you can calculate, substitute inside the equation, and find the car price. Is it clear? So take the car price as an example. Is there equation? Is there rule to tell you how to come up with the rule for the car price to predict? No. Since there's no rules, then we need to apply data mining. Is it clear? Yeah. So again, pay attention to here. For traditional, we have rules, we have data. We can produce answers. For data mining, we have only answers and data. So we need to use data mining to produce rules. Okay? So data mining is, the idea is to produce rules based on data and answers that we have. This is why we were looking for labeled data set to do prediction, because labeled data set means we have the answer, right? For labeled data set, we have the answer. We're looking for car price. That means the answer for the car price is there. The data is also there, like the car features. Is it auto, transition, gear, or manual, right? How many doors, the engine size, the power of the engine, and so on and so forth. So the data, like the features of the car, are there. The answer is the price for the car is there. but there's no rule. Okay? So there's no rules in order for us to apply to find or to calculate or to predict for other cars. Is it clear? Anyone still have a question? If you have a question, please, but after this, you should now already, if someone asks you, you can simplify. No need to write extract rules, and that one will look for underlying pattern. Up to you. But the point is, always, if you look to the simple example, will make everyone understand. Okay? Let's see if anyone has a question. Yeah, so no question. I hope now you should know already what we have. I mean, what is the difference between traditional programming and data mining? And please, every time, bring you a piece of paper. Maybe we're going to do like these activities every time. Let's take this as an example. So here we have, let's say we have a bunch of data, like -1, 0, 1, 2, 3, 4. Of course, this is very simple example. And here we have an answer. Now, the rules is this one, but pretend that we don't have this rule. Can you try to find out the rule from this data? Now, if you check here, you have -1. When your input or your data is -1, the answer is -3. So you may think that probably you need to do what? You may need to let's say, subtract -2 here, right? So you went from -1 to -3. And then, but if you look to 0, then 0, of course, when we cannot just simply subtract -2, then it's going to be -2. That means there's something else in here, right? Then how about if you multiply this by 2, right? Then it becomes -2. Then subtract with -1. So it's going to be -3. And then same here. If you multiply by 2, so 0 by 2 is 0, -1 is going to be -1, right? And so on and so forth. So again, 2 by 1 is 2, -1 is 1. So the point is, imagine if you don't have this equation, you can still try to find out these rules. By the way, some companies may show you some like those, I don't know what they call them, but something like to find the pattern inside the data. Not because of data mining, even if you are applying software engineer, has nothing to do. But because it's just to see how you can process, how you can do things, and maybe how fast you can find, let's say, some information from this data. Okay, so this is, again, quite simple, right? But we can still do it. I mean, we can just have a piece of paper, try different ways in order to find the rule. We can extract it by ourselves. But again, data mining can help us to extract this rule. Of course, here, very simple example. We don't need data mining, but let's say we're going to use it in order to understand how data mining works. So back to artificial neural network. Artificial neural network is a computational model inspired by the structure of biological neural network in the human brain. And it is powerful machine learning algorithm capable of learning complex patterns and relationship in the data. So the artificial neural network is actually very powerful. Is able to find complex rules extracted from your data. So here, take an example. This is showing you how neural network has started from the idea that here we have a neuron from the brain, right? And then these are the inputs. This is the cell for the neuron, or we call it the cell body. Okay, and then here these are the dendrites. These are the inputs for the neuron, and then we have the axon, okay, which is will actually transfer the signal out from the cell body of the neuron. So they came up with the similar idea. If we can create a structure, right, inside our application, which resembles the neuron. So here we have one node or one neuron. And then for dendrites, we have the inputs there. And here are coming our inputs to the neuron. Simply here, our features. Simply here, our features is going to be transferred or sent to the neuron. And then we need to apply some summation We need to take the summation for these inputs with multiplied by some weights. We're going to find out soon. And finally, we apply some function. We call it activation function. This activation function will give us the output. So again, I repeat, same idea. We have, let's say here, 1 neuron. And then we got some input. Simply here, the inputs are the value coming from your data set, from your record. And then we need to apply some summation, some equation. Just we're taking the input into consideration in some weights. We're going to find soon, later. After we find the result, then we apply some activation function. We call it activation function. This activation function will give us the last value, the output. And this output will be carried out. This can be the final destination. This is going to be the output for the final destination. Or maybe we're going to find this input, this output is going to be an input for next neuron. So we may have more than 1 neuron connected in sequence after each other. So either this is the final neuron we have, so this is the final output, or in other words, if this is like intermediate neuron, then the output from this neuron is going to be used as an input for next neuron. Okay, is it clear? So this is the idea all about artificial neural network, where we're trying to mimic the brain structure in order to resolve problems, in order to train the neurons to be able to resolve the problems that we have, okay? So the concept of perceptron, we call it perceptron, we're going to understand also soon, we have later, is founded by the possibility of emulating specific components of biological neuron, including dendrites, cell bodies, and axons, okay? Any question? So this is here, we have single neuron, but of course, we may have millions of neurons in our solution in order to resolve the problem that we have. So let's look into coding, how we can transfer this problem. So remember, we have this problem. We have this problem. How now we can build a system. We're going to provide the data and the answers. Right now, this answer means the label. We have the label here. And then the application should find for us the rule, or at least will be able to predict the output. Should be able to predict the output. For example, if we have input here 10, what is the output going to be? If you calculate on your side, or actually simple, let's say we got here value 10. If we proceed, let's say after we train our system, we can check if we have here value of 10. Then what is the output is going to be? 10 by 2 is 20 minus 1, 19, right? So let's find out. Just keep it in mind. Let's find out. So in order to build a neuron, or let's say neural network system, so we're going to use a package called TensorFlow, which is quite famous package available. So firstly, we need to create our model. So the model, you can think like we have decision tree, but now we don't have decision tree. We are building neural network. So we're going to use Keras is a library inside TensorFlow. So TF is just the alias name for TensorFlow. And then we are building sequential network. No need to worry much what here we have. Soon you will become more familiar to you. And then we're going to create one dense layer with 1 unit. So 1 unit means 1 neuron. Just so we have single neuron like the picture showed you earlier, just 1 neuron. And then the input shape meaning we are telling this layer, which is the dense layer, what is the shape of your input. Now look back to the slide. How many inputs we have, meaning how many features we have. We have only one, right? Only X. And X has only like X1, that's it. There's no X1, X2, X3, just X, one feature. So the input shape is going to be just one. This is why we say here the input shape is 1. Okay, so far so good. Again, if you have a question, you can raise your hand or you can write into the blog. Now, after we build our model, that's it. Our model only consists with 1 neuron. That's it. Only single neuron. And you're going to be surprised how this neuron is going to learn and will be able to find the value 19 that we already just calculated. So now we need to compile our model. So we need to compile. So we call the function compile. And then we need to specify the optimizer and the loss function. The loss function simply is like the one that we studied earlier to measure the performance the training or the learning performance of our neural network. So for example, since this is regression, right? Actually, this is an example for regression, correct? Is it correct or not? Example here provided is for regression. We have continuous value as an output. So we're not looking for classification, we're looking for regression. So actually neural network can solve both, can work for classification, can work for regression as well. So now we're working on regression. So we can provide telling the network or the neural network that the loss function that you need to use in order to check how good your training going on is the mean square error. Because again, it's a regression. Remember, we already studied in order to measure the regression performance, we have mean square error and others. So here we are using mean square error. And then the optimizer, because this is a training algorithm, so we need a way in order to train the neuron that we have here. And one of the famous algorithm is stochastic gradient descent, which stands here for SGD. So SGD stands for stochastic gradient descent. Okay, so this one will help the training algorithm in order for the neuron, in other words, in order to train successfully, correctly. Okay, there's some way it's going to go behind the scene. This is for the optimizer. So again, the optimizer is going to train the neuron. The optimizer is going to train the neuron. Along the way, the optimizer will depend on the loss function, which is the performance measure for our training. So all the time, SGD will depend to check what is the output, how the performance of the neuron is going on. Okay, is he becoming better, worse as we train the neuron? Then we provide the input. Here is our input, the values, same, just copy paste from the previous slide. And here is the answers. Now our objective is to build a neural network that is able to find or to predict other values. So that means it's going to extract the rules, and then later, once we apply a new value, predict should be able to find the correct answer. So finally, we call fit. So we provide the input and the answers, and then the epoch. Epoch later we explain, but simply is how many times the neuron, in this case, is going through the whole training data, 500 times. That means it's going through this data while training, how many times? 500 times. 500 times going to scan the input while training. Okay, any questions so far? So again, what is epoch? Epoch simply refers how many times you need your neuron, in this example, to go through your data set, your input data. Now, if we predict, I didn't put the answer here, but actually it's gonna showing you the result is about 18.9 or something. So it's very near to 19. And actually I already posted you the link for that one. You can try, but I don't have it here. Can someone post it inside the team? The link that I shared with you on WhatsApp today for the GitHub. If anyone can assist, or otherwise I can do it. Maybe just if someone can post it inside this recording, I mean the chat box. Nobody. Or actually no need, I can go to GitHub, but I need my account. So if you like to run this in Colab, so same example. So once you call predict, at the end, you see the answer is going to be 18.9. Okay. 18.9. So which is very near to 19, correct? So again, you see, just by using single neuron, we were able, the neuron was able to learn, right? And find, when we call predict, was able to find. Now, if you look here during training time, I think it's not showing, but you will see that the loss function has been calculated every time while the training is going on. Yeah, the training is not showing here for now. Okay, any question? If input shape equals 2 means, okay, if equal shape equals 2 means x squared. It depends, meaning it doesn't matter whether it's x squared or x cubic to the power of 3, it doesn't matter. It means input shape means how many inputs you have, how many features you are feeding the neuron. Because the neuron, as you check here now, the slide just shown earlier, you can provide, you need to specify about the input, right? Here. So you have input 1, input 2, input 3. Now, in our example, we had only a single feature. That means only we had N1. If we have 2 features, then we have N1 and N2, right? If we have 3 features, like X1, X2, X3, then we have here N1, N2, N3. Clear? So input shape refers how many features you have in your record that you're going to pass to the neuron. So in our example, we have only single feature. Okay? So meaning, during training time, what's going to happen? Only at first training is going to pass -1 and -3. After finish, then second round training is going to take 0 and -1. Then 1, 1. So only one, we have only one value is going to be passed at the time. Okay, so firstly, -1 is going to be passed to the neuron to train. After finish, it's going to pass second time 0. So only one value at the time. So we have, because only one feature. Okay, if we have 2 features, that means you're going to pass 2 values every time. Correct? So doesn't mean x squared. It depends. If you have x squared, this is x, then you need to calculate x squared. X squared, for example, is going to be 1, 0, 1, 4, 6, 9, and etc. So that means you're going to provide 2 inputs every time. So it doesn't matter whether it's x squared or x2 or x to the power of 10. It doesn't matter. You need to count how many columns, in other words, if you are looking to the CSV file, how many columns you have inside your data set, how many features. This will determine the input shape. Okay, is it clear? Any other question? So if you have a question, post your question. So again, this is just by using single neuron, only one neuron. We were able to train this neuron in order to predict the value for 10, which has turned out to be 18.9, almost 19. Okay, clear? Now, what is perceptron? Perceptron is very basic artificial neural network structure. Simply here, if you look, this is represent you a single neuron we have here. Again, this is like the previous example. Here, these are the inputs, x1, x2, x3, represent how many features you have. And then we have the node, as I said, is going to do some calculation, summation value. Simply, for each neuron, as we said, it has set of inputs, and it may have, sorry, one neuron has only single output. So in this case, for these, we call them connections, which simply they're going to transfer the input value. Now, these connections have some weight. They have some weight. So the weight means like how important this input feature is. Now, you don't need to set these. These are going to be set by the training algorithm. Firstly, it's going to initialize by some value, let's say random values, but along the way, in other words, the trained neuron, the training time for the neuron is all about adjusting these values, W1, W2, W3. Okay, so I repeat again, in training time, this is a single neuron. We have inputs, as we said, we're going to do some summation value to come up with some value. This value simply you're taking the input multiplied by some weight, let's say x1 by w1 plus x2 by w2 plus x3 by w3. You sum these values up, it's going to give you some value, let's call it z. And then we apply some function for the value of z, then we're going to get the output. Now, again, these weights actually during the training time is going to be adjusted in order for the neuron to learn, Okay, so how neurons work or learn based on the values that has been assigned to the weight. So for the previous example, what happened, every time you are training, these weights are going to be changed in order to fit or to be able to find you the correct output. Okay, we're going to understand that later soon, but just you can think of it, you are pushing some input, and then the neuron is going to do this calculation, apply some activation function, and then give you the output. Now, the output is going to be checked whether it's near to the correct output, the label that you have inside your data set or not. And based on this differences between the predicted value and the actual value, the weights are going to be adjusted. The weights is going to be adjusted in order to minimize the error between the actual value and the predicted value. Okay, so this is simply the idea. Now, perceptron, the idea of perceptron came in 1957 by this person called Frank. Also, it's called the threshold logic unit, TLU. The inputs and output in this model are numeric values, and every input connection comes with corresponding weight, as you see here. So in our previous example that we trained, we had only single input. Then we had only x1 and w1. We didn't have x2, we didn't have x3. Only x1, w1. Okay, because we had only single input feature. And then we calculate the weighted sum, this one, the value of z of these inputs, and then apply a step function. This is also called step function or activation function, which yield the final result as its output. Is it clear? So we have set of inputs simply is coming from your data set. Weights are going to be initialized by the algorithm, or let's say by the structure for the neuron. And then these weights are going to be adjusted along the way in order to minimize the predicted error output or the error for the output, to minimize the output error. Okay. Now, what is the activation function? One of the famous one is Heaviside step function, which is frequently used, or sine. Now, after we calculated z, this is for classification, let's say, then we check the value for z. If it's less than 0, then it's 0. That means class 0. If it's greater than or equal 0, then it's 1. Okay? Or you can take the sine function. Sine function can produce 3 outputs. So if it's less than 0, then it's -1. If it's equal 0, then it's 0. If it's greater than 0, then it's +1. Right? So after we calculate the z, which is the weighted sum for the input multiplied by the weights, then we apply the step function. The step function will give us the last output. Okay? So this is for classification, like an example where we get, let's say, the output should be 0 and 1. So 0, let's say, like yesterday work that you have done, 0 probably refer to the budget phone. 1 refer to the premium phone. Okay? So the step function will just check the value, and based on the value is going to determine whether the output is going to be 0 or 1. If the value is less than or equal 0, z, then it's 0. Otherwise, it's 1. Any question? If you have a question, you can post. So the perceptron, as we said, it has input, the weights, and then we apply the summation, which is the z value, the weighted sum. And then we apply the activation function in order to get the output. So again, this is another just, let's say, figure showing you the same thing. So we have inputs, and then we have weights. This will calculate the weighted sum. And then after the weighted sum is calculated, we apply the activation function. The activation function will determine the output. So y hat refers to the predicted output. So what is perceptron after all? That one was showing you the structure for neuron. So what is perceptron after all? The concept of perceptron refers to where you have one layer of TLUs, like this example here. These are the input, forget about them. So earlier we had just a single neuron, right? Now, if you have multiple neurons, that's fine, but all of them, they are in one layer, like here. Layer means, like you can think of it like a container where for this level, you have a set of neurons, okay? Like if you go to those people who grow or they look after bees, right? So there's many slots where the bees can actually make the honey. So each slot is like a layer. So you have layer 1, layer 2, layer 3, layer 4, and so on. So perceptron refers to a single layer of these. Whether you have one neuron or more, it doesn't matter, one TLUs or more. So this is each one of these refer to a perceptron. Okay, so the concept of perceptron consists of just one layer of TLUs. Can be one TLU, one TLU, one neuron or more. That's fine. Linked to all inputs. So look to this example here. We had single neuron, and this neuron has been connected to all the inputs. So here, if you like to write, this is X1, X2, X3, X4, right? Now, if you have more than one neuron, then also that's fine, but you see that each neuron is going to be connected fully to all the inputs. All the inputs. So this input has been connected to the neuron 1, neuron 2, neuron 3. And second neuron, same way. Okay, so here what it says, when every neuron, where each TLU linked to all inputs. Now, every neuron in particular layer is connected to the neuron in the preceding layer, that is the input neuron. Like this example has been connected to the input. But if you look here, we have two layers. This is one layer and second layer. So the first layer here has 3 neurons. The second layer has only 1 neuron. Okay? So in general, the neuron can be connected to the input, or like in this case, this neuron is going to be connected to the previous neurons as well, but it's not connected to the input. Okay, so only the current layer will be connected to the previous layer, whether it's input or other neurons. Okay, clear? So this is the structure for fully dense layer, where each neuron is fully connected to the previous neuron or previous input that you have. So input meaning the data that you have, your features that you are feeding to the neuron, or in this case here, this neuron is not being connected to the input, but connected to the output of the previous neurons that we have. So again, how many layers we have here? We have 2. These are the input, so don't be confused. These are the input. This is why I said you can write inside X1, this one X2, X3, X4, and then this is the first layer, okay, where we have a set of neuron, and then second layer, we have the output. Now, the problem in this one, if we have only single neuron, is the inability to learn complex problems, such as nonlinear problem. So if you have nonlinear problem, which is complex, this neuron, using only one neuron, won't be capable of doing this training. I mean, it won't be able to learn. Okay, so again, if you have nonlinear problem, complex problem, then single neuron won't be able to find the rules. Okay, so he's capable of finding, this neuron is only capable of finding linear problems. The problems that can be, let's say, linearly separable, like finding a straight line, for example, when we looked earlier for classification, or like what we call it, the decision boundary. Clear? Now, once we have nonlinear problem, then they found out that having only a single layer, like this example here, with only single neuron won't be enough, won't be able to solve the problem. So in order to solve the problem, they come up with the idea to stack multiple perceptron, meaning multiple layers, resulting in multi-layer perceptron, like this one. So we move from this structure where we have a single layer to where we have now here multiple layers. Okay, clear? So multiple layers is able to resolve nonlinear problem, complex problem. Okay, any question? No question? And this is, we call it MLP, multi-layer perceptron. That means you have more than one layer. Okay? Now, those layers of neurons that precede the output, we call it hidden layer, because this is the input, like a box. You provide input to the box, and this is the neuron is the output for the box. In the middle, you may have many layers of neurons, and these are, we call them hidden layers, because they fall in between the input and the output. Is it clear? So again, hidden layers refer to the layers that falls in between the input and the output. We call it hidden layer. So an MLP, or multi-layer perceptron, consists of one input, like this example here, often referred as pass-through layer. So this is why sometimes you see many people may have different names. And one or more intermediary layers, meaning those hidden layers. So in this case, we have only single hidden layer, okay? So known as hidden layers, and one last layer of TLUs, which is designated as the output layer. So when we have multi-layer perceptron, so at least you must have one hidden layer. If you don't have hidden layer, that means we go just to a single perceptron. Only we have single layer, like the example earlier here. So this one has only single perceptron, meaning we have only single layer of neurons with single neuron. When we move to multi-perceptron, that means we have more than one layer. So in this case, we have a hidden layer and output layer. Okay? Any question? What is the value of bias? We're coming into this. It's okay. Just now try to understand what we mean. Now, higher weight may be more important. Yes. Higher weight refers that this signal or this connection between two neurons, or maybe between the neuron and the input, has high importance. If low, let's say near to zero, that means there's very low or very weak connection between two neurons or the neuron and the input. Okay? Any other question? So the bias will come into it. Now, where deep neural network comes in. So now we know multi-layer perceptron. Now, deep neural network comes in when an artificial neural network is constructed with deep stack of hidden layers. Like this example, we have hidden layer 1, hidden layer 2, hidden layer 3. Of course, you can keep adding maybe 10 hidden layers, 20 hidden layers, and so on. So it becomes deep neural network. Of course, as you add more layers, the computation time is going to become longer. Okay? But of course, your also algorithm or your network, artificial neural network, will be capable to resolve more complex problems, but also can result in overfitting. If your network becomes so strong, okay, so powerful, then for a simple problem, then it's going to also may result in overfitting. Okay, so deep neural network, where we have many hidden layers inside our artificial neural network. So that's why they call it deep neural network. Now, how do we do training? Multi-layer perceptron training. How do we apply training? Now, in order to apply training, there's two ways: feed forward and back propagation. Let's start with feed forward to understand. Feed forward neural network is the simplest and most common type of neural network. It consists of input layer and one or more hidden layer as an output. Now, in feed forward network, signals flow only in one direction. As you notice here, the signals going, let's say here we have from input layer, and then go to the hidden layer, and then the result from the hidden layer is going to be transferred to the output layer. That's it. So it is just going in one direction. In this case, from the input to the output. Okay, so in feed forward network, again, the signals flow only in one direction from the input layer through all hidden layers to the output layer in a forward direction, hence the name feed forward. Okay, now of course, what's going on? Same idea that we explained earlier. We need to calculate the weighted sum, and then we apply the activation function. to get the output. So this is what's going to happen in the first layer. After you find the output is going to be transferred to the next layer. And of course, these connections have also weights. So again, for this neuron, you're going to again apply the weighted sum and again apply activation function. So activation function exists everywhere, except sometimes in output, we may not need activation function if we have regression. So this is the difference. In classification, we can apply activation function like we saw the sign or Heaviside, where we decide with the z value based on z value less than 0 or greater than 0 to decide the final class. Okay, but anyway, hidden layers, always they have activation function all the time. Is it clear? So again, feed forward, the signals is being transferred from the input layer through all hidden layers to the output, just in one direction. This is why we call it feed forward. Okay, any question? So here, same idea, if we have more than one hidden layer. So again, same. So the signal will transfer, notice here, from input to the hidden. After calculating the output is going to be used as an input for next layer. Also, you're going to calculate the output is going to be as input for next layer. And finally, you find the output for the final or the output layer. Okay, so feed forward, again, is only going in one direction. Clear? Simple. I mean, the concept is simple. Now, back propagation, actually, this is very important training algorithm, has been found in 1986 by these people. And this actually has made like the breakthrough of neural network. Before this, the efficiency of, or the accuracy of the neural network wasn't that good. Is one, like the training is not complete. So back propagation, simply what it does, it goes and feed forward. After finish, it go backward. So you have one forward, one pass forward, and one pass backward. This is what extra thing has happened in back propagation. So if you notice here, we have forward pass, like the feed forward. We're done. So now if you observe, let's start over. So now we go with feed forward or forward pass to make the prediction, the output, y hat. Then we use the loss function to calculate how much loss. And back propagation here comes in the picture. So earlier was just feed forward. Then back propagation will come here, where it will try to calculate to see how much error your model has committed. And based on this error, the model that has committed, it will try to adjust the weights. The weights for all. So here we have many weights. Weights on this hidden layer, first one, and then also weights on the second hidden layer, and also weight for the output layer. So these weights is going to be adjusted for one purpose, which is to reduce this committed error. Okay, so back propagation, how is going to determine how to adjust these values? By using the optimizer stochastic gradient descent. Stochastic gradient descent will determine how to tweak the weights for these neurons. Okay, is it clear? So again, we have feed forward, forward pass to calculate the output. After we calculate the output, then we compute the loss, how much error we have, like for example, mean square error if we are working on regression. And then we start the journey for backward pass, where actually here at this stage, and this stage where back propagation works, where you try to update the weights for all the neurons input. I mean the weights for all neurons, So notice now you go in backward shape, while along the way you adjust you update the weights. Now you repeat these steps with each batch of inputs until the network perform satisfactory. Okay, clear? So this is in simple word, what is back propagation? So again, we have two ways for train the network, because all the training is about adjusting the weights. Okay, the input you cannot change. Inputs will come from our data set. The output is also coming from your data set. The only thing you have is the predicted output that comes, but after you do the weighted sum, apply activation function, you get the output. Now, based on this output, you can measure the error between the predicted value and the actual value based on your data set. And later, after you calculate the loss or the error, then you start the backward where you try to adjust the weights for your neurons in order, hopefully, in next round, the error will drop down. Keep dropping down until your neuron or your model shows good results. Okay, so here also shows you what's happened. So during training time, what's happened? We are adjusting the weights. We keep adjusting the weights in order, once the algorithm has been trained, then we stop. Okay, and these are the final weights that we got. Now your friend asks about the bias. The bias is simply like a hidden input, extra input. Always, all neurons in each layer, they have extra one input. This is, we call it bias. So the bias is a constant term, the extra input you have, like in this example here. So here the values input coming from your data set, like value 1, 2, 2.1, 1.2, these all coming from your data set. But there's extra input, which is for the bias term, is being added. So after all, each neuron is receiving the number of inputs that are coming from your data set plus 1, which is the bias. So the bias is important. Why? It's the crucial component that allows the model to fit data more accurately. Actually, if you remember the equation for the line, for the simple line in high school, let's say where you have only x1, it's y equal a multiplied by x1 plus b, right? So b is the bias. We have some bias term inside the equation, which is resembled here in this one. If you remember, y was equal, let's say, a x1 plus b. Of course, a multiply by x1. Simply, this is your input. Okay, sorry, this is your input, x1 coming from your data set, and this is the weight. Let's say you have only single neuron, so that means you have one weight. This is the value we are after. We are adjusting this value every time in order to get the correct predicted value. So here, after all, we're going to calculate the predicted. This is B, is the bias. So inside the equation, we have bias. How to resemble this bias inside the neural network? We add extra input. And this value is always 1. Why 1? Not because of B. B is the bias here, the value. If you check this picture, the value here that's being adjusted inside this one, this is the bias. Okay? This is B. The one just now I mentioned. It's keep changing. But here always been multiplied by 1. And that makes sense. Because here it's just simply multiplied by 1. Right? So we are treating these as input. Now, if you like to think about it, these are input. This is x1, or maybe we have more. And then this is the one which is extra input given to the neuron. So after all, you are looking to find the weight A and B. The weights A and B. Is it clear? Does that answer the question for the person who asked about bias? So bias is extra term, constant, that we add to each layer of our neural network and has a value of 1. Okay, this one. Extra input. And we are after to find this bias value. And this is, as we said, crucial in order to enhance the accuracy for our model. Is that clear? So now for regression, of course, can be applied for regression and can be applied for classification. Now for regression, this is the common, or let's say the typical values that you can assign. Now for input, how many values, the input shape, it depends. Like if we are using MNIST, if you remember the handwritten digit, where we had 28 by 28 pixels, then the total you're gonna have 784. That means you need to put the input shape is 784. Okay, because you have 784 pixels from each picture that you have, which resembles the handwritten. And then hidden layer depends on the problem, but typically from 1 to 5, you can create hidden layers 1 to 5. How many neurons per hidden layer? Also typically from 10 to 100 you can have. So the units, if you remember inside TensorFlow code, you can have the value between 1 and between 10 and 100, the number of units. How many output neuron you need? You need one pair prediction dimension. So if you are predicting binary classification, then you can have single neuron is enough. If you have multi-class, then each class need one neuron. If you are predicting whether, let's say, the fruit is apple or orange or banana, then we have 3 classes. That means you need 3 outputs, 3 output neurons. Okay? Now the hidden activation function for the hidden layers, as we said, all may have activate. For hidden layers, all have activation. We use ReLU. We're gonna maybe talk about it during practical session. For the output activation, if you are doing regression, then you don't assign any activation. Just we take the final Z value that we calculated, the weighted sum. That's it. Okay? So none, or you can use ReLU or Soft Plus if positive output. So if you're looking only for positive, we have also special activation function you can apply. Or if you are looking for bounded output, you can apply logistic. Let's say with value between certain range. Okay, your output is in between certain range, then you have also special activation function to apply. So it depends, but generally, if you like just you have normal problem, then you can go with none. That means you have no activation function. But if that means the output can be, let's say, negative or positive. If you like to ensure your output is positive all the time, then you can use this activation function. It's called ReLU and Soft Plus. Now the loss function, you have mean square error you can apply, or you can apply mean absolute error, or you can apply another function called hover if you have outliers. If you suspect that you have a lot of outliers, then you can change from MSE to use hover. Or hover or hover. Okay, so this is for regression. Okay, this is just for regression, showing you an example what you need to decide. So if you decide, okay, how I can set up the input neuron, you need to check your problem, how many features you have. If you are working on computer vision, like face recognition, right, then you need to check the dimension of your pictures. And are they in 2D or 3D? So if they are 2D, that means 2 dimension, like this example here, 28 by 28, you said you have 784. If it's colorful, then you need to, what is the difference? It's going to be multiply by what? Anyone can tell me if the pictures for handwritten digit, in this case, are colorful. Then the size, the dimension, let's say how many, the width and height is 28 by 28. But if it's colorful, then we need to add the depth, right? And what is the value for the depth for a colorful image? How many colors for each pixel in colorful image you have? Sorry? 5? 256. Okay, any other answer? How many pixels represent one color on the screen? If we take 1 pixel from this screen, how many colors behind this to resemble one output? Yeah, 3. Red, green, blue, right? Correct. I mean, for colorful image, you have how many layers of pixels, right? You have 1 color for red, 1 color for green, 1 color for blue. If you mix them all together, you get the final color for inside the picture. So that means if, let's say, the MNest is colorful, then still 28 by 28 multiplied by 3, because each pixel or each, let's say, dot in the image is a resemble of 3 colors. It's a calculation of 3 colors, red, green, blue. Okay? You haven't used before Microsoft Paint, anything? Right? If you check Microsoft Paint, let's say if I take some picture, then any picture is just a resemble of 3 colors. Let's say I like to see what is this value for this pixel, and I click here. So you see that the value, this one, the color that we got, is the result of red, the value 80, for green 180, for blue 200. Okay, so again, for colorful image, we have the number of rows, let's say, and columns that multiply by 3, because each pixel has red value, green value, blue value. Okay, so if you take another color, should be different colors. Let's say we take gray. Then if you edit, then you're gonna see that the red now is 230, green 230, blue 230, which resemble this color. But if it's a grayscale, so if it's a grayscale has only one color per pixel. Okay, that's all. The value is between 0 to 255. That's it. Resemble between going from black to white. Okay, that's all. This is why if you multiply by 1 up to you, but it's gonna still 28 by 28 by 1 for grayscale, by color 3. Then you have the number of pixels, and then that will determine the input for your model, for your neural network. And then you decide how many hidden layers you like to have. So it depends on the problem that you are working on, but you may decide to go with at least one hidden layer, to 5, the typical, but you may go with more. For neurons, how many neurons we need to put inside each hidden layer, also you can decide. But the typical one is between 100 and between 10 and 100. Again, if you are working on regression, then how many predicted value you need? It depends on how many outputs, how many labels you have. Let's say, for example, let's say I'm looking for the car, let's say the house price and the size of the house. I need to predict the size of the house and the house price. Then I have 2 outputs, correct, for regression. Then you need 2 neurons. One neuron to predict the house price, another neuron gives you the output for the size of the house. Okay, clear. So again, how to determine, because the last layer, you need to determine how many outputs you're gonna have. So you need to check your problem. If you have more than one dimension, one label you like to predict, then you count how many labels you have. Let's say I like to predict the car price, and then I like to predict, let's say, the value for the car price after 5 years, and so on. So how many labels? Then you count. If you have 2, then you put output for 2 neurons. Each neuron represents 1 output. Okay? Is it clear? You have a question? No? For the activation function, as we said, for the hidden layers, we use ReLU. For output, we use none, because just we're looking for continuous value. So immediately we get it after we calculate the weighted sum. But if you are looking for positive output, to ensure that your outputs are only fall in positive, because if you put none, your output can be positive, can be negative. If you like to ensure that it's only positive, then you can use ReLU or Soft Plus. If you are looking for bounded output, that means you have only specific range for output you like to have. Let's say value between 1 and 100. Then you can go with logistic or tangent function. For loss function, we have MSE, mean square error, mean absolute error, and Hubbard. So these can be used when you suspect you have outliers. For classification, if you have classification problem, now the number for the input and hidden layers are same, like regression, whatever we discussed. So if you are working, let's say, on pictures to classify, let's say, face recognition, then I need to look how many people I'm looking to recognize in my photos. But first, for the input and hidden layer, I need to count. I need to look for my input. What is the size for my pictures? Maybe 32 by 32. Are they colorful or not? If they are colorful, then multiply by 3. Then I get the number of inputs. If they are grayscale, then just multiply by 1. That's it, the number of inputs. For the hidden layer, same, like whatever we discussed earlier in the previous slide, you apply the same. Whether it's binary classification, multi-label classification, or multi-class, it doesn't matter. You apply same thing. Now, for the output, if it's binary classification, then just you need 1 neuron, enough. If you are applying binary classification, then 1 neuron. Like the example yesterday. Yesterday in the practical test, you had binary classification problem. You need to predict whether the phone belongs to the category of budget phone or premium phone. It's binary, 2 classes. then it's enough to have a single neuron. So now if you like, when you go home, take again the data set for the practical test yesterday and try to apply neural network. How many output? Just one. Maybe now I try to show you an example for full network. If you have multi-label problem, multi-label binary or just multi-label classification, then one neuron per label, one neuron per label, okay? So if you have multi-label, then for each label, you need one neuron. If you have multi-class, same, also one neuron per class. If you have multi-class problem, let's say like face recognition, then how many people are included in your data set? You like to recognize 5 people only, or maybe your data set is about building face recognition to recognize 100 people. Then if it's 100 people, that means your output should have 100 neurons. Each neuron will refer to one person. Okay, will refer to one person. Now the output layer activation function, all of them you can use, or for binary and multi-label, you can use logistic function. For multi-class, you can use softmax. Softmax is special for the problem of multi-class because let's say I'm trying to predict the faces for 10 people. Then softmax, when I apply my model, my neural network, each neuron, as I said, is going to refer to one person, right? But this neuron actually is going to give you the probability. So let's say, what is the probability that this picture or recognizing person 1? And the second neuron is for the probability that picture belongs to person 2. The third neuron is about the probability of showing person 3. So softmax is going to ensure that if you sum up all the probabilities coming from all neurons, it's going to be equal 1. So you look just for the higher probability, which neuron is showing the highest probability, that means the picture belongs to that person. Again, why softmax? Because in probability, we like to have the sum of probabilities should be equal 1, right? So in order to ensure that the sum of probabilities coming from all neurons equal 1, then we need to apply softmax. For logistic, not necessarily. If you apply logistic, the output for all neurons, if you sum them up, won't necessarily be equal 1. Okay, and why we need this in multi-class? Maybe someone will ask why we need to ensure that the sum of probabilities for multi-class must be equal 1. Because we're looking for either, right? That means the picture cannot belong to 2 people, correct? It can belong only to 1. So I need to look for the highest probability. So the application should tell me, okay, the probability for this photo belong to person X1 is, let's say, 60%. Now the remaining 40% should go for the other people, correct? That means the picture belongs to person 2, let's say 30%. For person 3, let's say another 10%, which makes sense because we need to look for the highest probability. But logistic won't be granted to show you the sum of probabilities equal to 1, right? So maybe it's going to tell you photo belongs to person 1, let's say 60%, belongs to person 2, 60%. But already now 60 plus 60 has become over 100, becomes 102, right? So that's why we need to use softmax when we apply multi-classification problem. Now for the loss function, just you can apply cross entropy as loss function. Again, loss function is helpful to calculate the amount of error your network is committing. And why we need to calculate the error? Because back propagation, stochastic gradient descent, based on this value, is going to determine how much needs to tweak the weights for the neurons to be next time to drop this error down, to take this error down. Okay? Any question? Let's see if someone has a question. Okay, I understand the bias now. Thank you, sir. You're most welcome. Okay, epoch. May I know that is epoch referred to the no of times, the number of times the neuron go through feed forward. No, it's not about the number of times the neuron or the number of times you go through the neurons. It's about the number of times you go through the training data. That means how many times your neural network have trained on your data. Like now, if you do revision, okay, let's say for the course, for the material for this course, then if you say epoch equals 2, meaning you have gone through the course 2 times. Is it clear? You have gone through the course for 2. We were looking for a question. Oh, okay. Yeah, we were talking about epoch. So what is epoch? Epoch simply the number of times the neural network has gone through the entire data set. Okay? So again, like you think of it, the data you have for this course, the materials at the end before attending FA, let's say all the materials for this course you already have. Now, how many times you go through the revision, meaning you go the entire materials, how many times this represents the epoch. Okay? But we have another concept called batches. Batches simply is, let's say you have the materials, the entire data, the entire materials for this course. Maybe you decide today to go only with quarter materials, tomorrow with the second quarter, and so on. So the batch represents small size of the data set that's going to be loaded to the memory and used to train the model. Then after finished, then it's going to load another batch. Because loading also the entire data set to the memory is impossible. So we use batches. Like maybe you cannot finish doing revision or studying this course in 1 day. Then you can decide to have batches for this course. How many hours or how many materials or let's say chapters you would like to finish during the training session. Okay, during the studying session. Is it clear? Does that answer the question? So epoch, again, it doesn't mean how many times you go through the neuron. Okay? So if you say epoch equals 2, it doesn't mean you're going to go only through the neuron 2 times. Actually, you're going to go through the neurons how many times? If we say, let's say our data set has 500 records, and then we say epoch equals 2. That means you're going to go through the neurons how many times? 1,000. Right? You have 500. 500 is going to be used to train the model. Each record is going to be used 1 time to go through the network, the feed forward, and then do backward. Actually, if you check of it, even you may think like double. But anyway, I hope the point is clear. The epoch simply how many times you go through the entire data set. If still not clear, you can still ask. Now, I forgot to include one slide. I was showing you the epoch. But anyway, we still have some time. I'm going to show you an example. Right. Okay, here is an example if you like to look at. This is an example about data set of fashion. This is also MNIST, but it's not about handwritten digit. It's about clothing. So it's a data set about the fashion. Maybe I can show you a picture. This one. So it's about clothing. And then we would like to build using neural network in order to predict or identify whether the picture belonged as shoes or dress or coat and so on and so forth. Okay, so let's take a look. So here we load the data set is already available inside Keras, inside TensorFlow, in other words. So we load the data set. Then we take there's already have been provided. I mean, the people who work on this data set in Keras, they provided it as already prepared for training data and test set. So just we have the training data here and the test set here. And then let's say we take smaller part because this is the full training data. We need to take smaller part. Please, some people are talking. I'm not sure if the class is not important. I'm trying to explain to you something actually can be useful even for your FYP. Now you already done practical. Maybe this is not for you. Some of you may not be so important anymore. But if you are doing FYP, so this is still precious for you. So please, if you like to talk, maybe just use signals, signs. Okay, now if we look to the shape of our training data, now our data set is simply grayscale. And the size for each picture is also 28 by 28 pixels. So this is why when we look to the shape here, is 28 by 28. The first number resembles how many pictures we have. So simply we have 55K of pictures. Okay, going for the training data. Each picture has a size 28 by 28. Since they are grayscale, otherwise if they are colorful, then it should be comma 3. Okay. We check the data type is just a unit, unsigned integer. Now we need to do normalization. Remember normalization, feature scaling. So we need to ensure that all pixels have the value between 0 and 1. This is why we divide by 255. So we take down the value, and instead to be value between 0 and 255, it becomes between 0 and 1. We normalize all pixels. Then this is just a sample to show you. This is the first picture inside the training data set. And for the Y train, here shows you the classes because this is classification problem. Okay, so it shows you the classes. Actually, we have 10, if not mistaken. So either the picture can be t-shirt or trouser or so on and so forth. So we have 10 classes. So this is multi-classification problem. Multi-classification problem. You can get the class names from this object. We already prepared because the data set originally doesn't have the names. It just shows you the class number, just number. So here this person has put the actual name for each class. Now this is our data set. Let's see how we can do modeling. This is, by the way, same if you are doing face recognition in simple way. But of course, again, the pictures are in grayscale. Then we start same way like what we have done earlier. We have sequential model. Sequential model means we have a full dense layer. We are creating, let's say here, dense layer model, and then we have dense layer here. But anyway, first we create our input layer. Now this is a bit different, but easy to understand. So the first one is input layer. The input shape, since our pictures is 2-dimension grayscale, so they are 28 by 28. Okay, so that's why we put the input shape here is 28 by 28. And then we need to flatten. Flatten, why? Because the dense layer, in order to learn, the input has to be each picture, guys, but just your one are chatting, please lower down your voice. They're distracting us and other people. So the input shape, again, the input layer has input shape 28 by 28. Again, you need to check your picture size in order to determine. For this example, you have 28 pixel by 28. And then we need to flatten. Flatten means we need to make each picture represented in one vector. This is how dense layer works. You cannot provide the 2D picture directly to the neural network. So you have to flatten. Meaning, if you like to understand what does flatten exactly do, if we take MS Paint again, let's take some picture. Okay, now flatten, what does it mean? Let's say this is our picture, but we need to make it as vector. So what happened? That means I take, let's say, the first row of pixels here. Let's say this is represented one row of pixels. Okay, so here this is the input before flatten, and here I'm going to draw after flatten, how it's going to look like the picture. Again, it has to be a vector, meaning I'm going to take, let's say this is the first row. Let's say this is the first row of pixels. Then I copy paste, let's say for now. And then I put it here. But of course, you're not going to see. So better let's ignore this. Take the first row. Consider this is the first row of pixels. Then you are putting it here. Then you take the second row of pixels. Let's say this one. For the sake of argument, you put them next to each other. Okay, and so on and so forth. So you need to flatten your picture to become a single dimension, where all the pixels, 28 by 28, 784, should be inside one vector, one line. The picture, how neural network is going to learn, not the way like you think in your mind, I need to take the 2D picture and throw it to the neural network. You have to make it in one line. So all pixels has to be set in one row. Then I take all the pixels, I feed forward, or I feed it to the neural network. This is why we need to add flatten. So flatten is just like a function, is going to help us to make this, since this is 2D, two dimension, we have rows and columns, is going to become only rows. Each row has how many pixels? Simply 28 by 28, you have 784. Then we start preparing or feeding to the next layers. So now here, we start here, we have how many hidden layers? Hidden layers? 3 or 2? Because remember, we have input layer, we have hidden, we have output. So the last one is the output. That means we have 2 hidden layers. Okay? Now each hidden layer, how many neurons it has? 300. This is up to you, you can decide. So here, the first hidden layer has 300 neurons. And the activation function for them is, or are ReLU. Then, after this dense layer, there's another dense layer. So we have 2 hidden layers. The second hidden layer has how many units? How many neurons? 100. The activation function is also ReLU. Finally, this is the output layer. The output layer. So we put units equal 10. Why 10? Because how many classes we have for this data set? We have only 10 classes. As we said, 1 neuron per class. So we have 10 classes, so we need to put equal 10. If you have data set with 20 classes, then you need to put 20. Okay? If you have only binary classification, then you put only 1. So you need to determine the right number for the output based on the problem that you are working on. Then the activation function, since this is multi-classification problem, according to the slide, we need to use softmax. If it's multi-classification problem, then you use softmax. If it is a multi-label, then you can use logistic, for example. Okay? Yeah, that's it. So here we prepared our network. So again, the input layer has the shape, then we need to flatten, because as we said, the dense layer works only on vectors, where each picture represented in one line of pixels. Then we start to feed here. This is the first dense layer, or the first hidden layer. So we have 300 neurons. Now here, the output is based on the activation function that we're going to apply. Now the hidden layer, this following hidden layer, where it takes its input from, where the input is coming for the second hidden layer. Now the first hidden layer, we already understood, coming from the pictures after flattening them, after we make them records, vectors. But how about the second hidden layer? Who's going to feed the second hidden layer? Who's going to feed, or what are the inputs for the second hidden layer? Yeah, so the output from the previous hidden layer. Okay, so here, how many output we have? 300, because we have 300 neuron. So we have 300 output is going to be fed for the following hidden layer as an input. And then also this layer, second hidden layer, has how many outputs, or how many neurons? 100. So the 100 output is going to be as input for the following output layer. And finally, the output layer has only 10 output, 10 neurons. Clear? So this is showing you the result. You can call summary for your model. So it's sequential. And then we check, we have flatten, which simply is after the input. Since we have 28 by 28 pixels, so has been flattened to 784. None, why none? Because it depends on how many pictures you have. But the structure for the neural network already determined here, this side, by the number of neurons, based on the number of pixels that you have decided to have. None, because we don't know yet how many pictures we have. Only when fitting time start, only the neural network will know. Then we have the dense layer, which is the first hidden layer. We have 300 neuron. Okay, and following that, the second hidden layer, we have 100 neuron. And finally, the final output, we have 10 hidden layer. Okay, so here showing you the number of weights, the parameters that each layer has. So for this only network, imagine how many values the neural network is going to tweak, to learn, to train. While training, how many weights or values is going to tweak around? The total number of params, 266,000 plus. So you can imagine for this example, how many like this one. Of course, we're going to have too many of them. Let's say this is A1, then A2, A3, A4 until A. How many? From A1 until A266,610. So all these values are going to be tweaked around in order to be able to classify correctly the 10 classes. Okay, so here the input layer after flattening, and then become 784. And then the input, of course, is the output of the previous one. So this is the first hidden layer. So the input, how many inputs we have? 784 based on the flattened, 28 by 28. The output is going to be 300. And then the 300 is going to be input for the following hidden layer. And the output is the number of neurons we have, which are 100. And finally, the output layer, the number of inputs coming simply are the output of the previous layer. And since we have 10 classes to 10 neurons, so we have 10 outputs. You can get the weights from each hidden layer by calling get weights. You see, these are the weights for each hidden layer. These are the biases. So we compile our model. Since we're working on multi-classification problem, then the loss function can use cross entropy. Cross entropy has many ones, sparse categorical, and there's other ones as well. So we apply, but anyway, we are using cross entropy. Then the optimizer is stochastic gradient descent, the metric to evaluate, in this case, is accuracy, because we're working on classification, right? So classification, we use the performance measures, is accuracy. Then we compile our model. We provide same, actually, these two are equivalent, these two lines. This is to convert to one hot encoder anyway. Ignore about this. Finally, fit, we provide the training set and the Y test, the X train and Y train, and the epoch is 30 times. That means our training data has how many pictures? 55,000 pictures. Epoch here is 30. That means it's going through the entire training data set 30 times. That means 50K, 55K by 30, then you can count how many times these pictures are going to be fed to the neural network, and you can provide the validation set at the same time. So it's going to use the validation set to calculate the accuracy based on the validation set. So here, if you check for each epoch is going to calculate and show you the accuracy result. So you notice that the accuracy at first, it was 0.8, 80%. But you will notice that it keeps increasing. As you keep going in each training epoch, then the accuracy is keep increasing. So now it has become 86%, it's almost 87, but it may drop down. It doesn't matter, but the point is overall should keep increasing. Until the last epoch, then we reach 88 or about 89% accuracy. Okay, and the loss function, you saw it dropping down because the loss function is about the term of error. So we started with high error, 0.7, and keeps dropping down until the last epoch, it has become 0.22. The loss function is going to be used by stochastic gradient descent, right? As we said, because we need to tweak the weights inside the neural network. Then here is showing you the loss and validation loss value for training and validation, and the accuracy for training and validation. Now, in order to make prediction, let's say here we have 3 pictures, or let's say if you have 1 picture, then you can call predict, and then you get the probability. Here we are looking again because regression, sorry, not regression. We're looking for classification problem, and we have used softmax. So softmax should give us what is the probability for each picture belong to each class. So now if we look here, how many pictures we have? 3 pictures, right? We took 3 pictures from the test set to do prediction. Now each picture can be one of 10 classes because we have only 10 classes. If you count here, how many values we have for each row? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now based on this, the training model, the neural network tells us that the highest probability for the first picture is belong to the last class. What is last class? You can check back. The last class is ankle boot. And actually it's correct. This is the first picture because from this is from training, wait, not from the test. But anyway, it's going to be the ankle boot. You can check. I'm not sure if it has shown the picture here. Yeah. So the first picture is ankle boot. And according to the probability produced by the neural network, the ankle boot had the highest probability, meaning the neural network is going to give you probability for each class. What is the probability that the first picture belongs to the first class, second class, third class? And then based on the highest probability, we can determine the final class. The second picture is pullover. Then the corresponding neuron or the output for this one is 0.99 and so on. Okay? So this is about neural network. And here we have another example. You remember California housing, also using regression. But just interested to show you the difference here in modeling. So it's already been normalized earlier. This is another way. But anyway, the point is here. You notice for layer, this one, since we are working on predicting the house price value, so we need only 1 neuron. Then there's no activation. So you can just assign the number of units, meaning the number of neurons with no activation function. Okay, I hope that helped you to understand in simple what is neural network. And it's quite powerful, as already know, like such as ChatGPT is an example of neural network. In the meantime, let me just see if anyone has a question. No question. With Auntie. So what you guys have discussed just now with Auntie, you can go follow her and see.